Hi and welcome everyone to part 3 of my series of presentations about the best methods for converting aliphatic alcohols into alkyl chlorides. This video is about the use of Phosgene as deoxychlorinating reagent. Because of its low cost and because reactions with Phosgene only generate hydrogen chloride as waste, Phosgene is often used in industrial large-scale deoxychlorinations. Unfortunately, Phosgene is highly toxic, but not as lachrimatory and irritating as thionyl chloride, and may therefore be inhaled inadvertently. It should therefore always be handled with extreme care. Phosgene is about 100 times more toxic than carbon monoxide and about 10 times more toxic than chlorine or hydrogen sulfide. Phosgene is prepared by chlorination of carbon monoxide in the presence of active carbon. Although the starting materials are inexpensive, high security and purity requirements can drive up the production costs. Two alternative reagents often used in the laboratory are the liquid diphosgene and the solid triphosgene, prepared by radical chlorination of methyl chloroformate and dimethyl carbonate. Both reagents are converted into phosgene by heating or in the presence of pyridine or other catalysts, and should therefore also be handled with great care. A number of strategies have been developed to circumvent the use of stoichiometric amounts of phosgene. These include the photolytic in situ generation of phosgene from chloroform, the in situ generation of carbonyl bromide from carbon monoxide and bromine, the deoxychlorination of carbamic silyl esters for the preparation of carbamoyl chlorides, and the chlorination of carbonic acid thiol esters for the preparation of chloroformates. Alcohols are converted upon treatment with phosgene into chloroformates that undergo thermal or catalyzed decarboxylation. Like chlorosulfonates, chloroformates can be converted into alkyl chlorides with retention of configuration by an SNI mechanism, in which a tight acylium chloride undergoes substitution from the same site as the leaving group. The decarboxylation of chloroformates proceeds, however, more smoothly upon catalysis with some chloride salt, and inversion of configuration is then often observed. In the absence of catalysts, chloroformates may also undergo beta elimination and yield olefins upon heating. This may also be suppressed by using a suitable decarboxylation catalyst. The thermal stability of chloroformates depends a lot on the carbocation forming ability of the oxygen-bound alkyl group. Simple unbranched primary chloroformates can be heated up to around 140 degrees Celsius before decarboxylation sets in. Secondary chloroformates can already decarboxylate at around 100 degrees Celsius, and benzylic or allylic chloroformates start decomposing at about 50 degrees Celsius. Tertiary chloroformates cannot be stored at room temperature, and for the amino group protection of amino acids as terts-butylcarbamates, Boc anhydride is used instead of terts-butyl chloroformate. Deoxychlorinations with phosgene can be conducted without any base or in the presence of bases. In the absence of bases, the reaction mixture turns strongly acidic, and only acid-resistant solvents will remain unchanged. Ethers, esters, nitriles and ketones are less well suited for such reactions because these will often undergo acid-catalyzed hydrolysis or condensation reactions. Catalysts able to promote the decarboxylation of chloroformates include pyridine hydrochloride, weakly coordinating ammonium chlorides, such as tetrabutylammonium chloride or hexabutylguanidinium chloride, other amine hydrochlorides, DMF and phosphine oxides. This is an example of the uncatalyzed thermal decomposition of a secondary alkyl chloroformate. Even at 100 degrees Celsius, only 20% of the starting material had reacted after 5 hours, and a 2-to-1 mixture of alkyl chloride and olefins was obtained. The stereochemical outcome of the uncatalyzed thermal decarboxylation at 130 degrees Celsius was mostly retention of configuration, but partial racemization was also observed. In the presence of 10 equivalents of pyridine, the decarboxylation proceeded much faster than without pyridine, but the secondary alkyl chloride was formed mostly with inversion of configuration. Inversion was also observed when 0.5% of hexabutylguanidinium chloride was used as catalyst. With this catalyst, the decarboxylation was complete after 10 hours at 80 degrees Celsius. Also, when DMF is used as catalyst, the decarboxylation of chloroformates proceeds with inversion of configuration, as shown here. Only a slight excess of phosgene and 10% of DMF were enough to convert methyl lactate into the corresponding chloride. The configurational stability of alpha chloroesters or ketones, however, is not very high, and such compounds may racemize if heated for too long in the presence of bases or even chloride. In this example, alpha chloropropionate underwent significant racemization upon heating in the presence of only 0.5% of a guanidinium chloride by repeated SN2 reactions with chloride. Such racemization can sometimes be prevented by constantly removing the product from the reaction mixture by distillation. Also, cyanohydrines can be converted into alpha chloronitriles by treatment with phosgene, as shown on this slide. Direct chlorination of nitriles usually yields mixtures of mono and dichlorinated products, which can be difficult to separate. So, what are the potential side reactions? As with hydrogen chloride and thionyl chloride, if the reaction mixture is allowed to turn acidic, all kinds of carbocation-mediated side reactions can occur, such as rearrangements, cyclizations, eliminations, or dealkylations. Diols and amino alcohols may readily form cyclic carbonates and carbamates upon reaction with phosgene, which may not react further. If tertiary amines are used as auxiliary base, the intermediate chloroformates may also react with these tertiary amines and yield, after amine dealkylation, stable carbamates. I'll show you some examples of direct amine dealkylations and oxidations by phosgene in a minute. Then, phosgene, as all strong electrophiles, may oxidize other compounds by single electron abstraction. Bromide ions, for instance, can be oxidized by phosgene to elemental bromine, which can then brominate olefins or electron-rich arenes or heteroarenes. Ketones can be converted by phosgene into vinyl chloroformates or, at higher temperature, into vinyl chlorides. Ketones are therefore not suitable solvents for reactions with phosgene. Another functional group that readily reacts with phosgene is the amide group. NN-dialkylamides or ureas are converted into chloroiminium chlorides, which can act as reactive deoxychlorinating reagents themselves, but non-alkylated amides are usually converted into nitriles, as shown here. Under forcing conditions, nitriles may even react further and undergo alpha chlorocarbonylation followed by cyclodi or trimerization. Thus, such reactions should not be allowed to proceed for too long, unless such cyclic oligomers are the target product. Although tertiary amines are often used as auxiliary base for acylation reactions with acyl chlorides, this isn't a good idea, because tertiary amines can be dealkylated or oxidized by acyl chlorides. In particular, strongly electrophilic acyl chlorides, such as phosgene, trichloro or trifluoroacetyl chlorides, can bring about such reactions. Benzylic or allylic amines are, of course, particularly sensitive, as shown on this slide. Treatment of benzylic amines with phosgene at room temperature led to extensive debenzylation after only 1 hour. Also, methyl groups can often be selectively cleaved off from tertiary amines, for instance by treatment with chloroformates. This is an example of the oxidation of triethylamine by phosgene. Most of the initially formed chlorocarbonyl ammonium chloride underwent deethylation by nucleophilic attack by chloride, whereby ethyl chloride and diethyl carbamoyl chloride were formed. Carbamoyl chlorides do not hydrolyze readily, and in this instance still 18% of carbamoyl chloride was isolated after treatment with an excess of methanol. Another fraction of the initially formed chlorocarbonyl ammonium chloride, however, underwent elimination of hydrogen chloride and carbon monoxide, whereby an iminium chloride was formed, which was deprotonated by the excess triethylamine to yield an enamine. This enamine was chlorocarbonylated once or twice by Phosgene, and treatment with methanol yielded the observed acrylates. Here are some more examples to help you get a feel for the scope of this reaction. The next video is about the use of phosphorus chlorides as deoxychlorinating reagents. These are very popular for laboratory preparations because of their high reactivity and selectivity and the simplicity of their safe handling if compared to Phosgene. One important drawback is, however, the generation of phosphorus waste, which can be difficult and expensive to dispose of.